Now there is a relation between the focal length and radius of curvature of spherical mirror, and as you know that this relation is r is equal to 2f, that is radius of curvature is 2 times the focal length. Now in the revised syllabus which is given to us, in that it is written that explain r is equal to 2f. Now explain means if it is asked that you derive, then you can derive by a simple geometric understanding. Okay, say for example you have this concave mirror. Okay, try to understand this figure and just orally you can understand very easily. It's too easy. Okay, this is your concave mirror and this is the incident ray which is incident at an angle theta. Now try to understand how this perpendicular is drawn from the center of curvature. Now try to understand this as a part of sphere. Now this is the sphere, and if you draw the radius, that is line joining the center to any point on the circle, will be perpendicular to the tangent. So this part becomes the perpendicular at a point of incidence, and this is the ray which is incident. Now it will be reflected at the same angle. So the angle of reflection is same, and that is also theta. So this must be very clear to you. Okay, this is incident ray. This is the perpendicular drawn at a point of incidence, that is at point M, and it is making an angle theta with that perpendicular. And as you know, angle of incidence is equal to angle of reflection. So this angle will also be theta only. Okay. Now the total angle here, this angle will be equal to 2 theta. Okay, it will be equal to 2 theta. Okay. Now as you know that these two lines are parallel to each other, and this becomes the transversal, and therefore these angles, try to understand this way, these angles are making z and they are alternate angles. Okay, so here the angle is theta, then this angle must be theta. And if you try to understand this part, this is also a z. Okay, again I am drawing it for you. Okay, see this type, this angle I am talking about. Okay, this is also another z. Okay, alternate angles, and this angle is 2 theta. So this angle must be 2 theta, as these two lines are parallel to each other because they are parallel rays, and this becomes the transversal. Okay, so the angles are very clear to be for you to understand. Okay, so different angles here are shown. Okay, here theta is the angle of incidence and MD is the perpendicular from M on the principal axis. You can see. Okay, here for our concave mirror, if we take the understanding, then consider a ray parallel to the principal axis, strike the mirror at point M, and CM is the perpendicular to mirror M. No need to explain this part, that of convex mirror, you just understand one, because this part is as such, we just have to remember the formula. Okay, let theta be the angle of incidence. Okay, here theta is the angle of incidence. Okay, then you can see here MCP is theta and MFP is theta, that is shown here. MCP here, which I have shown, MCP is theta and MFP is 2 theta, that I have explained. Okay, MCP means this angle, MCP. And if you talk about MFP, then this angle will be 2 theta, that I have explained how they are becoming theta and 2 theta. Now just we have to consider two triangles. Try to understand. Very easy. This triangle you consider. Okay, here DP is very small. So as such this D is on P or P is on D, this is a very small gap. So you just try to consider this triangle MDC. In this triangle tan theta, as you know, tan theta is opposite, that is MD upon CP. Okay, and in the smaller triangle, this triangle I am talking about, that is MDF. In triangle MDF, you can take tan theta is equal to MD upon FP. Now you can see here this theta is as such very small, 2 theta will be again very small. So theta is equal to tan theta in radian for very small angle. So we can easily write tan theta equivalent to theta. So we can easily write theta is equal to is tan theta is equivalent to theta in radian, as theta is very small. So theta can be equal to, instead of tan theta I am writing only theta. Okay, and that becomes MD upon CD. Theta is MD upon CD, opposite upon adjacent. Okay, for this triangle. And instead of tan 2 theta I am just writing 2 theta. For that it is again opposite, that is MD upon, here adjacent is CD. So that is, sorry, FD it is, CD FD. Okay, now see C to D is as such equal to C to P. Try to understand, D and P are very close to each other. So that C to P distance is equal to radius of curvature. So it is approximately equal to radius of, sorry, not MD, it is CD. Okay, not the MD. MD will remain as it is. Instead of CD we have to write R. So MD is remaining as such, as it is. And C to D, this C to D is nothing but equal to C to P, and that is equal to radius of curvature. So theta is equal to MD upon R. Similarly, here 2 theta is okay. MD upon, what is F to D? F to D is nothing but equal to F to P only. FD or FP both are same, because this D to P distance is very small, and F to P is nothing but focal length, that is F. Now you just have to compare these two equations which we got. Okay, these two equations just we have to compare for theta. So here in the first equation, theta is MD upon 2R. You can see theta is MD upon 2R, and here MD upon 2F. Okay, then left hand side will be same. So theta is equal to MD. Okay, theta is equal to MD upon, it is R. Okay, and for another equation, the theta for focal length, it will be MD upon 2 times the focal length. Now if you just compare these two equations, then MD will be cancelled out, or you can take ratio, whatever you want to take. Okay, so MD upon R is equal to MD upon 2F. Therefore R is equal to 2F. Hence it is proved that radius of curvature is 2 times the focal length. Okay, remember this equation, many numericals are there. Okay, now we take the sign convention for the discussion of the spherical mirror and the reflection by the spherical lens. Now you can understand this part better. Okay, this is very easy. You must have discussed this in your 10th standard even. Say for example, you have this concave mirror. Okay, now all the distances are measured from the pole. That is your first requirement. You have to keep the zero of the scale at the pole. Okay, so all the distances are always measured from the pole of the mirror or the optical center of the lens. If you have lens, then pole is said to be optical center for the lens. Okay, so you measure the distance from this point pole. Okay, now the distance measured in the same direction as in the incident light are taken positive, and those measured in the direction opposite to the direction of incident light are taken negative. So try to understand this part. You just have to consider the axis of our graph. This you consider as x-axis. This is for remembering the sign, okay, and this is the y-axis. Try to understand. Now if the object is kept here, then if you want to measure the distance of the object, then you must have to start from pole, this point, and you have to keep your zero of the scale here, and if you are measuring the distance in this direction towards left, then those distances are taken negative. Okay, so when the object is here, okay, yes, incident light will be like this. So you are measuring the distance in the opposite direction of incident light. Therefore, that distance has to be negative. Okay, try to understand this direction as such for our x-axis. If you consider 0, 0 at pole is a negative x-axis. So distance in this left direction will be always negative. And if you are measuring the distance in the direction of incident ray, that is towards right side, if you are keeping your zero of the scale here at the pole, then direction of measurement, if it is in the right hand direction, is the distance, that distance is positive, because x-axis is on right hand side, direction is positive. That way also you can remember, distance on left side are always negative from the pole, and distance on right side are taken always positive from the pole. Okay, now the next part, if the object is somewhere here and if you are measuring its height, then if it is in the upward direction of the principal axis, then this height is taken to be positive. If the height measured in the downward direction of the principal axis, then this height is taken negative, because in this way also you can remember, this is y-axis, this is positive y-axis if 0, 0 is taken here, and this is your negative y-axis. So measurement in downward direction will give you negative value, measurement in the upward direction will give you the positive value. Okay, so all the distances you can measure from the pole. Okay, and you can remember that these are the axes, that is x-axis and y-axis. Distance on left hand side, if they are taken, then they are negative, because here negative x-axis this is. Okay, and this is your positive x-axis. So distance in this direction will be positive. If the image is somewhere here, then the image distance will be positive. Say for example, image is formed somewhere here, then image distance is measured from pole, and this distance would be positive. Okay, height in the upward direction is positive, height in the downward direction is negative, because upward direction will have positive y-axis, and in the downward direction there will be negative y-axis or negative y coordinates. Okay, these are sometimes also known as Cartesian sign convention also, because we are using the Cartesian coordinate system for the reference. Okay, thank you very much.